Hello everyone, thank you for attending my talk. My name is Gregory Essertel and I'm going to present our paper named On-Stack Replacement for Program Generator and Source-to-Source Compiler. This work was a collaboration with my colleague Ruby and my advisor Tiark from Purdue University. Source-to-source compilation is a widely used approach for implementing domain-specific languages, and explicit program generators are often used to implement high-performance libraries because they can provide specialized code generation facilities in ways that are out of reach for fully automatic compiler. While in many cases code is generated and compiled offline and then available for future use, there are also important use cases where code is generated and compiled on the fly and then run once and discard. This means that the compilation process is part of the runtime of the service. So in this particular example, if we generate a low-level C code for the SQL query that we have on the left, the compilation of that C code will be part of the runtime, and that is something that we need to take care of. So we look at what were the compilation time of multiple SQL query that we took from the TPC-H benchmark. We generate low-level C code from these queries and compile them using different compilers. And we can see that the mainstream compiler and TCC have an order of magnitude of difference in compilation time. So let's take a deeper look to one query to see how it looks when we actually execute the code that has been compiled. So if we take TPC-H Q6, we see that TCC is the fastest and has an order of magnitude of difference between it and GCC-03, but we also see that the -0 of GCC is almost a 2x between it and GCC-03. When we run that code on an input of 100 megabytes, we can see why the compilation is much longer for higher optimization level. The binary generated is actually much more efficient. However, when we look at the combination of compilation time and runtime, this is not the highest optimization level that comes first. We can see that actually the GCC with flag -01 is the best. So, following the same idea that the first virtual machine did with tier execution, so as a reminder, the virtual machine was first using an interpreter that had a low latency but a low throughput, and then if a function was used multiple times, that function was compiled just in time and then used to speed up runtime. So here, in this case, we can use TCC as a low latency and low throughput interpreter by compiling very fast the code, starting to execute the code that was compiled, and when a code with better optimization level is available, we can swap to it. And we can see that in every cases, that idea go faster than using the GCC directly with any of the flag, but even in the -01, we see that the configuration TCC then GCC-01 is the best runtime for that particular query. So looking a little bit closer at the shape of the generated code, we see that when we compile SQL queries, the code is mainly composed of long-running while loops. And long-running while loop is exactly what current virtual machines are optimized for doing on-stack replacement. So the idea would be to target such language, for example, Scala. So we generate, as well as the C code, we generated a Scala code that we run on the virtual machine, and it should take the power of on-stack replacement as we have seen before. But we see that we are still not as close as we are to the C code, for example, for I/O reason. So we still want to generate C code, but have the power of OSR. So let's take a look at an animation that illustrates the solution that we are proposing. As we have seen previously, loops is the focus of our idea. So we are going to illustrate our idea using a generic loop. From an initial loop, we are generating a different version of the loop. So we start with loop version 1 that is going to then be compiled and optimized to a binary, and then starting the execution. During the execution of the first version, a second version of that loop can be generated and then compiled and optimized with different optimization or speculative optimization. When the first version can detect that the second version is available, then we can trampoline to that second version. And in order to preserve the semantic of that switching, it must happen between two loop iterations. And that process can be executed as many times as needed. And we can even go back to previously compiled version if they are better for at a given time. So let's take a look at the generic transformation. Still transforming a loop. So we want to transform a loop given a sequence of condition and transformation for each I. So we each of the function I are a transformation of the body of the loop that is equivalent to the original body of the loop under the condition that that CI is true. And when we invoke the oracle select, it's going to select the code such as the CI is currently true. So we can do optimization and also de-optimization by going from one transformation to the other. We don't have to go in chronological order. In order to avoid to have to select the oracle at each loop, we can actually select a while loop that is going to execute until the condition CI is true, or we are at the end of our loop. If we exit the loop, depending on the condition, the initial condition, if it's true or false, we can say we are done or not. And if we are not done, we are asking the oracle to select another version of the loop. And we can also take the loop out as a function to make it a little bit more clear. And depending on the target languages, we may have to do a closure conversion if the target language do not handle top-level function that way. And we see that the transformation only use the target language primitive. There is no need to represent any intermediate representation. Therefore, any later optimization in the compiler do not have to use to handle the OSR primitive because they are none anymore. So let's take an example. Here we have a while loop that compute a dot product. And we can generate two loops from that. The loop one, which is the basic dot product that we had before, and the second one is actually a vectorized version of the loop. And maybe that loop takes a little bit longer to compile for some reason, but we are going to put them in two different compilation unit. Therefore, we can start to execute the loop one and then jump to the loop two. And here is also the version with the closure conversion. The details are not very important, but it was just for the example. So as a summary, for each of the the sequence, we need to make sure that the transformation are equivalent to the original body of the loop under the condition that the condition CI is true, which means that we can have assumption. As long as they are true, we can keep using that loop. And every time at each iteration, we need to make sure that there is at least one such condition true. We cannot generate multiple code that at one time none of the conditions are true, therefore there will be no code to execute. So let's take as a first use case, which is tier execution that we have been talking a little bit so far. And if we go back to our modelization, in this case, the function are actually the identity. We don't actually transform the body of the function. We keep it as true, as the same, but we are going to compile them using different compiler. Therefore, the CI are just true if the compilation of that given piece of code is terminated. And so here is an example of the C code, and we do not show the logic of loading the new code, but most languages have a way to load code at runtime. And here is the output we have on a few different query. So on the left, the left column, we are using 100 megabyte as input, and on the right column is 300 megabyte. So we can see that in all situations, the OSR version of tier execution are better than the none that just using GCC, and the difference is a little bit more pronounced for smaller input size. And in all situations, it seems that TCC with GCC-01 is the best configuration we can have. Here there are two other queries which have the same kind of behavior. Another use case would be speculation, low-level speculation. And so in this case, we take the same piece of code, but we compile it with different compiler flags at the lower level. So for example, we could have a loop that is doing a conditional aggregation. So if a value is positive, we aggregate it. And we are going to use flag to vectorize this loop or to not vectorize it. And we need to specify a selection heuristic, and we are going to say, okay, if the hit on that loop is higher than a cutoff, that means that the selectivity is pretty high, therefore vectorization should be better. And by doing experiment, we can see that when the selectivity is 0, the code that is not vectorized is actually much faster because loop prediction would be very good at the CPU level. But if the selectivity is 100, the vectorized code is actually much better and 4 times better because of the length of the register is 4 times. And as we can see, the OSR pattern is always picking the best available code. And especially for if the cutoff is equal to 15, which seems to be the selectivity at which the both vectorized and non-vectorized code are the same, we see that it always picks the fastest code. Another use case is high-level speculation. In that code, we are generating different code for each loop with different assumptions. So for example, when we have an hash map, we can optimize that hash map for 2 keys or 3 keys, or just use a generic hash map. And for example, using assuming that there are 3 key or 4 key or 5 key or 6 key, and actually looking at running code when there are 3, 4, 5, 6 or 25 different key, we can see that when we do the correct speculation, the code is around 10% time faster than before, and otherwise it's almost the OSR fall back to the generic version, and we are not losing any performance. So as a summary, we reduce the overhead to introduce an extra compilation step by using OSR, and we develop a simple model of OSR for source-to-source compiler that can open any kind of new optimization, high-level speculation or low-level speculation, and we implemented it within the LMS framework and evaluated it with Flare that generate low-level C code from SQL queries. Thank you for attending, and I will be around to answer any of your questions. Thank you.